All right, guys, so we've already looked at graphing linear inequalities. Now we're going to take a look at what's called systems of linear inequalities. If you remember, we've dealt with systems of linear equations. It's similar to that. Instead of having just equations and graphing the lines, because we know all the lines would be solid when we graph them, now we're dealing with graphing a system of linear inequalities. So basically having boundaries, but that could also be a solid or a dashed dotted line, but then also having shaded regions based off of each inequality that's written. So giving more conditions to a situation or a scenario that we might be in. So to start with, again, if we're going to deal with a system of inequalities, just like a system of equations, we're going to be dealing with two or more inequalities that share the same variables. Okay, two or more inequalities that share the same variables. Now, when we're going to graph these systems of inequalities, basically you just take one linear inequality, you graph that all the way through, even doing the shading, and then you graph the second inequality and do the shading with that. Where the shadings overlap, you're going to have a solution set in that area. So what we want to do first when we're graphing, again, the linear inequality is you want to get the linear inequality into what's called, again, slope-intercept form. So if you recall what that looks like, y equals mx plus b. So we have m as our slope, b as our y-intercept. So we want to make it look like this form. Of course, the equal sign changes because it's actually going to be an inequality symbol in that spot. Same idea though. Then secondly, you need to determine, are you going to be graphing a solid or a dashed line? Is it going to be broken or is it going to be solid, right? So if it's solid, you're going to use symbols. It will have symbols such as greater than or equal to or less than or equal to. Okay, it's going to have the line underneath. So if it does have that little line, remember that's the equal to part, then you know you're going to graph a solid line. If for some reason it's a greater than or a less than, you know you're going to be dealing with a dashed line. Okay? Once you've determined that, then you can go ahead and graph the line using the slope and the y-intercept. Remember, we start with the y-intercept and then we apply the slope to that intercept point, whether it's going up or down and then left or right. So rise over run for your slope. Finally, you're going to shade above or below the line, depending on which inequality symbol you're looking at. Now remember previously I mentioned that you should isolate the y variable by itself. Once you isolate it by itself, if you have it on the left-hand side, then you'll be able to determine easier if you're going to shade above or shade below. Okay, but that's the basic steps there. So let's put that into practice with two examples here. If we first look at example 1, we're going to want to make sure we identify the starting point and the slope for both of the inequalities that are written there. Okay, so when we do that, we know that the first one, where it's x is greater than -2, you're going to have a slope that is undefined. Why is it going to be undefined? Well, basically, x is greater than -2. If you recall previously in the other presentation, that it's going to end up giving us a vertical line. And if you remember Slope Dude, when he was talking about things, when he had a vertical line, it was undefined, right? Then your starting point is going to actually be at -2. The reason we say it's going to be at -2 for this, again, it's not going to cross the y-axis, so it's not going to have a y-intercept for this one, but it's going to be a vertical line that crosses through -2. So I know this is a special case, and sometimes it's kind of hard to understand that, but the x value is always at -2. So it's always going to be at -2, so it won't cross the actual y-intercept. So this is a special case, special scenario. Now with the second inequality though, we see that the slope is -3/4. Now that's what you're used to seeing and then the starting point is 1. So you can go ahead and you can apply the starting point and use the slope with that one. So if we look at the first one and graphing it, we're going to have a vertical line where it passes through -2. And because it says x is greater than -2, we know we're going to shade everything to the right because it's greater. When you shade to the right, the numbers are greater than -2 for the x on the x-axis. So it'll look something like this, okay? And then when you graph the next inequality, again, it was a negative slope, so we know the line is going down from left to right. Starting point was at 1, so down 3 to the right 4. And in this case, you see how the y is to the left there, and it says y is less than or equal to. So if it's less than, it's lower, it's below it. You can shade below that line. Now, you have graphed both inequalities, and the solution set is going to be in that green section because it needs to satisfy both inequalities, not just one. So remember, with equations, systems of equations, we looked for where the two lines intersected, and that was the point that you could use in both equations. Now with the inequalities, there's an actual region that we have. So there's multiple points for solution here, and it's within that region there that is green. So that's where your solution set would be found. So the points within there would satisfy both of the inequalities. The second example, similarly, in this case, there's a special situation or a special case where you have this y is less than 3. So if we were to graph that, we know that we're going to be looking at a horizontal line. So in that situation, we know the slope for a horizontal line is 0, goes straight across. And the reason I put starting point at 3 is because in this special situation, it's always going to be across at 3. Right? So your line will always be across at 3. But is it going to be dashed? Is it going to be solid? Well, we see that it's less than. And since it's less than, we know that there's no equal to with it. So it's going to be a dashed line straight across. Now, again, if we look at the second inequality really quickly, you notice the slope and the starting point there, the slope being 2/3 and the starting point being -1. So, like we said, y is less than 3. It's going to be a dashed line straight across at 3. Again, y is to the left, which means that if y is on the left-hand side, you can say when it says y is less than 3, where are all the values of y that are less than 3? Below the line. So we shade below the line. Then we apply the same practice we would with the linear equations. We're going to use the starting point at -1 for the second one and the slope of 2/3. So we can go ahead and graph that. It's a solid one because it was equal to. We have y is greater than or equal to. Y is on the left-hand side by itself. Y is greater than or equal to. So greater than means above it. We shade above. And then our actual solution set for this is where the two shadings of intersection are, which is the green area there. So we have our solution set there. So your systems of linear inequalities is very similar to systems of equations, except now we have different regions for our solution set. So if you get used to graphing one inequality by itself, now you're just graphing a second one on the same graph, and that's pretty much all there is to solving and graphing a system of linear inequalities.